So, hello everyone. This is the talk about Qt graphics. Yeah, the title has nice thing. It says nice things about accelerated this and that. So basically what we are going to look at is a bit like what are we working on in at the Qt company in Oslo in the graphics team. And we're going to look at some of the ways to do UIs with Qt. And also in the second half of the presentation I will talk a bit about some of the changes or new things we are planning for Qt 6 or maybe even a bit before. So I'm Laszlo. I'm working in Oslo at the Qt company, which was before what was known as Digia, before it was part of Nokia, and of course before that it was Trotec. Yeah, there will also be some live coding and this and that in the presentation, so we'll see how that goes. So yeah, what we're gonna look at is, of course, a very quick history of Qt. By the way, some questions. So, who of you know what Qt is? And yeah, I think some of you may have been to Volker's talk earlier this day. So, how many of you have been there at 9 o'clock at that other Qt talk? Well, of course, Volker was there. Well, that's good. Then something else. So, who's familiar with the differences between widgets and Qt Quick? Oh, that's a lot of hands actually. And finally, who's familiar with the basics of a modern accelerated 3D graphics pipeline? So I'm thinking of a pipeline where you have some vertices coming in and there's a vertex stage and then there are other things. Good, so there are some hands about that too. That just may be relevant because we're going to talk about later Opengl, which is of course used in a lot of places in Qt, and also some other APIs later on. Yes. Yeah, something about me, although that's not that important. So I've been working in Oslo since 2013. Back then, of course, this company was called Digia. I've been actually working with Qt also when I was actually working at Nokia, although originally I come from the Symbian side of things. And yeah, doing Symbian apps, then some UI framework stuff. And then when the Nokia acquisition came through, then yeah, I started working more with Qt. And then yeah, building UI stuff on top of Qt, mainly for Symbian. Then of course later I was working on Qt itself, so on the Symbian port. Then actually between these two places I've been also spending some time in Trondheim at ARM, where they developed the Mali GPUs. And there, yeah, during that time I've been working on implementing Opengl ES3.0 for the Mali 600 series. Yeah, that's enough for now. So when it comes to Qt, well, probably many of you have an idea what this is about. This is just a screenshot from Qt.io. It's not perfect, but it gives a quite good overview of the things Qt is used for, or the areas Qt is used in. Because on the left there is that thing with application UIs, and this is the traditional Qt story that you can do cross-platform applications, between Windows, Mac, Linux, and other platforms. Then the other thing is this embedded story. So you use it to create all sorts of devices. But of course devices typically mean, although it doesn't have to include the screen, but typically it still has a screen. And so you typically, in the simplest case, there's embedded Linux and some other OS. You boot up into a Qt-based graphical application, and in the simplest case that will render everything, and that's that. In the more complex cases, of course, it could be that you are composing together the output of multiple applications. And if it's a good system, those are, of course, all Qt-based apps, but anyway. And, of course, there is the third pillar, which is the mobile. So, of course, today, we have support for Android and iOS, so desktop, mobile, embedded. We say this a lot, so these are the three important areas. And yeah, there are some examples of industries there, so there's a lot of focus on automotive today, but of course there are plenty of other places where Qt is used.
Is the microphone supposed to work?
No,
okay.
You are only hearing because this is only used for the recording, so I was hoping that it would be sufficient. Or am I not loud enough? Oh, okay. So finally, it's another thing is that of course Qt traditionally has been a bunch of libraries, like a framework. But of course, nowadays we have tools, so think of Qt Creator, the IDE, and also there's an increasing focus on design tools, so things which are designer friendly. So instead of writing C++ or QML or whatever, these tools are supposed to be usable by designers who don't necessarily know how to code. So because there's a lot of interest in this in automotive and elsewhere. Oh yeah, of course, Qt. It's good to notice that it's pronounced Qt, which many of you probably know. The thing is that, of course, many people in North America in particular like to pronounce it as Qt, which is fine, but the official way is Qt. And it's a capital Q and a lowercase t, because it's just, yeah, that is the official way. So sometimes you see it in Qt with all caps and whatnot, which is fine, but yeah, that might mean other things. So jumping straight into things, I'm going to skip the well-known parts like Trolltech. Qt was started to be developed in 1991. So the important part here is that in the Trolltech era, the main technology was probably widgets. So like the classes like QWidget, QPushButton, Q other things, widgets, subclasses of QWidget. The screenshots going clockwise, well, that just tries to give an idea of things that was done in those days. So that thing here, that's a Qt 1 application, which somebody ported recently to Qt 5, which is pretty cool. But yeah, widgets, buttons, so that's where the whole thing is coming from. Then, yeah, of course, probably early in the days, there were already things added to help designing things, so you don't just describe your widget-based UI from C++, but that's a widget designer which still exists today. It probably doesn't get too many new features, but it's there. Okay, then there's a screenshot of Cdiz. So of course, people have been building quite complex systems. That's the screenshot of Cdiz 3, I think, which was mostly widget-based, I suppose. And of course, this is, yeah, these are from desktop, like Windows, Linux, Mac. But of course, already in those days, like the embedded story is important. So in the that thing comes from the documentation, but it really sums it up pretty well. So imagine the case that you have an embedded Linux device. There is no windowing system, so all you do is that you have a Qt application, and what you do, well, in those days, fvdev was not that deprecated. So for example, you could typically open /dev/fv0, do some ioctls, and then write some bytes to it, and that's how you wrote something to the frame buffer. So of course, Qt took care of that for you. So yeah, that was a pretty nice way to create these single-purpose devices. Of course, already in those days, accelerated graphics was important, but I don't really mean things like OpenGL or stuff like that. I'm mainly thinking of these 2D accelerations. So for example, PowerVR had proprietary APIs to do accelerated blitz. So I'm thinking of those type of acceleration. So yeah, and finally, of course, there was Qtopia, whatnot, what also Vulkan mentioned in his talk, that people have been building pretty complex things. So this was actually shipping on a bunch of handheld devices. So of course, Qtopia was more like a full suite of things, not just the framework itself, but also things that are built on top. So I promised some live coding, so it won't come as a surprise that we're going to write a hello world with widgets. But the important thing is I'm not really showing you what QWidget is, because many of you know that, but then we're going to just step into that code, because what I want to show is that how that gets rendered. So we jump straight to Emacs, just because we are not starting with creator right away, because why not? There. We'll see how visible that is. So let's do a project file. So we are still using QMake, even though you might know that Qt has these ideas about migrating to CMake. So by the time Qt 6 is out, it could be that the build system is CMake, not QMake. But that's not really important right now. Oh yeah, that's better. So the interesting theory is that, okay, I'm going to pull in widgets. So that just means that, okay, now we can include stuff from the widgets module, and presumably that will also link to a library. So of course, Qt Qt contains many modules. So, you know, Qt Core, Qt GUI, Qt Widgets. Of course, in practice, these are typically like shared libraries. So we want to just pull in what we need here. OK, that's fine. Now, the simplest thing. So what I want to do is just to have a window with a button. So that really shouldn't take more than 5 lines, except that I can't type. So of course, there's this nice application object. Oh, yeah. Thank you for reminding me. So this is already a full-blown Qt application. I'm not going to run it yet, because then, OK, what happens here is that we enter an event loop, and then, of course, I would need to kill that application because it wouldn't exit on its own. So instead, let's add the widget. I'm just using QWidget, because that in itself is basically sufficient. It can serve as a window. Yeah, the thing gets compiled somewhere, and is this the right place? Oh yeah, so that's a window. Now, of course, OK, this can be resized, it can be closed. So when we close the last window, we will exit the event loop, and that's how then we will return from main. Well, that's fine. Now let's add the button. So yeah, how surprising. It says click me, and the parent will be that widget. And OK, let's just print something when it's clicked, just so we can demonstrate signal and lambda connections. So we connect to the QPushButton click signal and do something like I will just use qdebug, whatever clicked. I hope this can be compiled. Yeah, let's launch something. So this is a debug output, because I was too lazy to change this to a console app. So OK, now there's a button at there, position 0, 0. Doesn't look very good, but the thing works. Well, that's good. Now, the interesting question is that how was this thing rendered? Because what we have here is in the window, there is some sort of gray background, which presumably depends on the palette and whatnot, and then there's a button. We'll get here later. So let's just open it up in Qt Creator this time. And let's hope that the debugger will work. Where was this? And this. Yeah. Yes. So I just open that profile. Hopefully it will scan and find everything. Oh yeah, let's get rid of this. Yeah, it still works. So how do we render that button? So there is this joke in Qt that, I mean, inside the company, that there are so many ways to render a button. And of course, from time to time, there are new ways introduced to render a button. So QPushButton is a widget. And those of you who have written custom widgets before, who of you has written a custom QWidget before? So who subclassed QWidget? OK, that's good. So there is a paint event, which is a virtual, and you can override it. Now I'm going to look at the implementation of QPushButton's paint event and put there a breakpoint and run this. So, ooh, even resizing works. It's amazing. So what happened here is the core stack is not that interesting, although if you look at it, you see like there's an expose event. So what's happening here is that when we are showing the window, so the native window, which is created behind the top-level QWidget, so presumably it gets shown, and OK, in Qt that gets translated to an expose event. So now we know that we need to render something, some content. Then we go through several layers of exciting stuff, like backing store and things in widget private, which doesn't really matter. But of course, if you look at things like draw widget, paint siblings recursive, that's quite telling. And finally, we send a paint event to the button, like QPushButton. Now, what is this? So what is QStylePainter? So that's a subclass of QPainter. So who knows what QPainter is? Or who knows what either Cairo or Skia or is because it's more or less it's a similar thing. So of course QPainter is an API in Qt that can render things like points and lines and rectangles and, of course, more complex things, polygons, arcs, even rounded rectangles. And, of course, you can images. So really, this is this traditional drawing API. And yeah, so Qt, back in those days, even today, widgets, of course, use this to really render their content. Now, how does this really work in practice? So there's some styling thing here, which we're gonna kind of ignore here. So it's enough to say that we will invoke some draw control thingy. Never mind this. Let's jump straight to the command style. And the interesting thing here is that a button is, of course, we don't draw a button. So, of course, the typical thing is that it's broken up to smaller parts. So, you know, maybe it's a text, then inner parts, frame, and so on. So you can see that, of course, this is, again, we call draw control. Of course, the recursive call. And, of course, these pieces may be also broken up to smaller parts. Push button label. But the important thing is here is that eventually we will end up in a place which is platform specific or style specific. So this is still in the common code, but if I now jump to something called QWindow style, which is presumably a style for you know, Windows when running on Windows, you see that, for example, this we end up eventually here when we draw this element called frame focus rect, and this is indeed does nothing but uses QPainter. It sets a pen, brush, draws rectangles. If we would go here, this is something for the radio buttons, you know, those circular things. You know, there are ellipses, whatnot, so everything in widgets gets drawn like this. Of course, the goal here is to get something that follows the native look more or less. So, yeah. So this is cool. Basically, it's a QPainter command stream. But there's another thing to this, which of course you don't really think about much when using Qt because it hides this from you. But then how does this end up not on the screen? That's not the right thing here because we just want to get to the native Windows APIs, like some GDI stuff. So to quickly look at that, I think the best thing is, okay, let's just restart that and just simply step into this thing here. Yeah, QPaint step out in, because eventually we will begin painting on something. And two interesting concepts. Yeah, this is QPainter begin. This is not very relevant yet. So, but the two important part here is the QPaint device and the QPaint engine. So one very common pattern everywhere in Qt is that things have multiple backends. So for example, QPainter, that's the API, but of course the underlying implementation, well, that there can be multiple ones. So the QPaint engine is what really provides the implementation of, you know, how you execute the draw rect and other things. And of course, the paint device is the target. You know, the widget is a paint device, so it's why you can kind of open a painter on a widget. But the interesting part here is this. So we query a paint engine from the paint device. And okay, there's some magic there. That doesn't matter because the main thing here is that, okay, we give the platform plugin the ability to really override and return a customized paint engine. But the common case is this, that you end up in using the Raster paint engine, which is one of the, I don't know, kind of the crown jewels still in Qt, one of them since the Qt 4 times. So this is a pure software implementation of all this. How do we draw rectangles, lines, text, so everything which is in QPainter. So there, no acceleration is involved, it's all done in software. And yeah, so yeah, that's one of the key components. Now, okay, we have that. And the final piece is that what do we render into? Because you see that there is this is a Q image, and it's not even clear how do we get there. So the Q image, that's typically a container for image data. So, you know, I create a Q image of size 640 times 640 480 with a format like ARGB32. Then, of course, in most cases, it will just malloc 640 times 480 times 4 bytes, and then, yeah, that's the storage area behind that Q image. Or, of course, it can also adopt an existing area somewhere. So, you know, then it won't, allocate new space, but it will simply wrap and then not own that existing data. And that is actually will be a key to in many cases. Yeah, so QImage, how do we get that? So we won't debug it any further, but just very quickly look at the thing here called the backing store. So in the stack trace, you saw that somewhere there was references to some QWidget backing store. So backing store is something that's associated with, in the simplest case, top-level widgets. So a top-level widget in this case was this W. And of course, that has a native window, like in Windows, of course, there will be an HVND window handle somewhere, and there's also a backing store. But the backing store itself, that's a very simple thing. It can do things like resize, flush, some scroll things. But this has platforms per platform implementations. So this is the thing which we refer to as QPA, introduced in Qt 5.0. So many classes in Qt GUI have a QPlatform equivalent, so like QPlatform backing store, which is full of virtuals. And this is then implemented in the various platform plugins. So in Windows case, that's done in the Windows platform plugin. So I will just quickly jump to the Windows backing store, and we're going to look at two things. What do we paint into? So this doesn't matter. The interesting part here is this. There is some helper class, QWindows native image, which we can jump into. And finally, this is the first part when actually we see some native things, because you can see that now this is Win32 GDI stuff. So for example, here we create a DIB, device-independent bitmap, which is a Windows thing, concept. And we also get a pointer to the data, so the pixel data. And when we have that, it's pretty cool, because we, of course, have a device context. We do a select object. No need to go into GDI details. And also create a QImage, which, of course, just uses the bits, this existing pointer. So, of course, when now we target this QImage with QPainter, the results go into that memory block, which is, of course, which was created for us by Windows when we created this bitmap. So yeah. And finally, the final piece in the puzzle here is the flush in the backing store. So in the simplest case, we end up here. So unsurprisingly, there is a blit. So of course, there's this native image sync at the DC device context, and we blit from there to the Windows DC device context. Of course, in the more complex cases, when we care about alpha and blending and whatnot, we go through a more modern thing, which is update layer window indirect, but of course the end result from our perspective is the same. So there's a blit to the, and then things show up. The rest is up to Windows, what it does, what it does with this stuff. So, okay, what's this? So it's a screenshot of the things we saw. Oh, and that also demonstrates that Qt Creator has split views, so it's almost as good as Emacs. But yeah. But anyway, so the point here was this. So in that box there, I was trying to summarize one typical path from widgets to the, well, in this case, windowing system. The problem is that to everything I say here, there are usually 5 or more exceptions, because on some platforms things work differently and there are special cases, so that's graphics. But this on Linux, like X11, the concept, it works more or less the same way. Well, it's a bit different, but yeah. So widgets, there's a styling, QPainter command stream that ends up somewhere. Yeah, like in some sort of image. So this is all good, and now we move on to the Nokia days. And you probably know the story. Nokia acquires Qt, and then, of course, the desktop story is important, so Windows, Linux, Mac, because that's needed for developer tools, and of course also to allow people to develop at least some parts of their phone apps and test them out on desktop. But of course, there's Symbian, MeeGo, and later some other projects, which of course try to then utilize Qt. The two interesting things here is that then, how do you build the iPhone killer UI? Because this is 2008, and you know the iPhone was out there. And how do you create a nice, fluid, 60 FPS, touch-friendly UI? And the bit of a bad thing here is that, of course, multiple approaches were tried over time. So, of course, you could take widgets and just style them. So you use QPushButton, but then it has a custom style. And yeah, that's one option. But of course, it's limited when it comes to animation and whatnot. You know, you can't really freely transform widgets. Then things were attempted to be built upon this graphics view framework, which is a framework inside the widget framework. So graphics view itself is a widget, which is sort of a canvas, which can then handle primitives like text, line, of course, image, polygon, and a few other things. So the idea here was that the Nokia teams, Symbian, Migo, would build their widget sets on top of graphics view from these primitives. And then this would give them, yeah, some advantages because, you know, things can be more freely transformed within that canvas. The problem was that, meanwhile, QML, the first iterations of QML, this declarative UI description language, appeared, which was QQuick 1, that's what the QQ1 thing refers to, which was originally, I think, kind of going through graphics view, which is cool, but the problem was that now, do you want to build your buttons with C++ using the graphics view APIs, or do you want to build your buttons in QML? So there were some problems with the story. And on top of that, obviously the performance, mattered here. So in addition to, of course, doing stuff in pure software, so QPainter gained the ability to gain more paint engines. So in Symbian, there was a lot of focus on OpenVG at the time, which is an accelerated vector graphics. So that's more like a 2D-ish drawing thing. That's also a Chronos standard like OpenGL. Whereas, of course, Migo and others were betting on OpenGL ES2, which was like which came out in 2008. It is the spec. The problem is that, as we will see later, this whole QPainter-based architecture was not always performing as good as it could. So in addition to all this, QQuick 2 ended up not being based on QPainter, but the idea was that it would use directly OpenGL ES2. Before going into the QQuick thing, let's finish the history lesson. So of course then in 2012, Digia, Finnish services company, acquires Qt, which later, and the Qt part became independent in 2016. So this is now an independent company headquartered in Helsinki. It's publicly traded on the Helsinki Stock Exchange. The main R&D offices are still Oslo, Berlin, and Oulu. But the headquarters are officially in Helsinki. So the interesting things here are, well, of course, the mobile. So the Nokia stuff goes away, and instead there are ports to Android and iOS. And of course, there is a lot more focus on, obviously, the commercial licensing, because we need the money so that we can have an office and people in Oslo. So obviously, Qt is dual licensed. So, you know, open source under various licenses, and of course, there's a commercial business. And there's, of course, a lot of focus goes on embedded, because, of course, more and more people want to build various devices. And, of course, QQuick 2 is an essential piece, because now it's based on OpenGL, OpenGL ES2, and, of course, many of the devices released in this time frame, of course, they have some sort of GPU, so OpenGL ES2 is fairly widespread. But it doesn't just mean Linux, because then we have things like QNX integrity, you know, other type of OSs, which they love in some places like automotive, so they have some advantages in few places. And we also have some increased focus on tooling. So I mentioned this is a designer-friendly tooling, so that you can design, you know, your QQuick UI in a tool that's usable also by designers. So let's forget widgets. Let's do something with QQuick. I'm going to be cheating here, so I'm just using the Qt creator templates, creating an empty QQuick application called quick test. What is this? We don't care about these. So this generated me a profile with lots of nonsense, but what matter? Okay, we pull in quick, and we have a C++ thing, and we have a QML file which will be embedded into the executable via the QRC, the Qt resource system. So presumably there's a QML file somewhere, which is this. Oh, and of course the main CPP looks like that. but this is not the right main. Yeah, it sets up the QML stuff, and then yeah, we'll load that QML file. So this actually runs on its own. It shows nothing. If you want to show anything, we're gonna add something. So let's have a red rectangle, because we have this thing that in graphics you always have this red rotating rectangle. So of course, you know, it's quite easy to lay out things in QML, and of course it has things like property binding. So of course the property values could be expressions referring to each other, and of course you can also easily animate things. So let's animate the rotation for, yeah, 2, 360, duration, loops infinite. Oh yeah, so yeah, that's there. Let's make it let's make it so that it's in the center. Awesome. Let's add some text. Again, anchors are powerful. Oh, good. So there's some tags, there's some rectangle, everything is fine. Now, the interesting part is that how is this rendered? Well, that has nothing to do with the stuff you saw before. So if you, for example, fire up render doc, which is itself that's a graphical debugging tool, so it can capture frames from OpenGL, Vulkan, these 3D applications. So this itself, the UI is done with Qt widgets, I think, but that's, of course, just a fun detail. So if I now run this through this, and capture a frame. So of course, this is now pure OpenGL. So we could see that, of course, I closed it. So there is, yeah, that's the output from the fragment shader. So of course, there is geometry. There is triangles all over the place, or triangle strips. So that is the rectangle in that frame. And of course, this thing here, well, there's just a bunch of triangle for the text. And of course, there's a vertex shader, fragment shader. So, you know, it's, yeah, pretty simple, just 2 draw calls, but yeah, still completely OpenGL based. Okay, that's cool, but why is this good? Which is the point of the whole exercise. So this is good because between the QML document, what you saw there, and the final OpenGL rendering, how we get there, there is something called the scene graph. So I'm just setting an environment variable and hoping to get some useful output here. So the scene graph, you know, the Qt scene graph, this is mentioned in contexts all the time, in various contexts. So in this QML document, so behind this, there's this scene graph. And this is what the Qt renderer works with. It doesn't really know anything about QML and rectangles and that stuff. What it sees is a tree where the leaves are typically geometry nodes. So it has vertex index data, you know, the positions of those, for those triangles. There's a material, which is a vertex shader, fragment shader, and related stuff. And then, of course, these are under various transform nodes. So in here, you can see that, well, you can't see it, but I'm telling you that, for example, rotate that rectangle. So that rotation matrix is actually in this transform node. Or, of course, this is the text. And, yeah. Of course, you have some additional node types like clip node, because sometimes we need to clip either by scissor or stencil, or an opacity node, but not much else. So that's the scene graph. And the new thing here in Qt 2 is that since we have this, now we can do much better decisions when it comes to, you know, generating the OpenGL draw calls. Because unlike QPainter, which was this blind draw this, draw that kind of stream on every frame, we now have a scene graph which is persistent. So of course in every frame, you know that what parts have changed. Maybe a new subtree got added, maybe a new subtree got removed. Some property changed, but of course you know that some parts have not changed, which of course allows us to then reuse, you know, the graphics resources like buffers or textures. And since you have this structure of the scene, you can do clever things like, you know, merging geometry together. So of course, let's add another rectangle, which I'm just gonna make red, just to make the, yeah, just put it to the top left corner. Does this work? Yeah. So there is now 2 rectangles, and in the frame graph, you can see there are 3 geometry nodes. But the fun thing is that in an ideal case, well, normally you would expect 3 draw calls. But of course, if in an ideal case, this could be done in 2 draw calls, because this first one now, this includes both. That's hard to see there, but of course, there's the triangles for the first rectangle, and there's the other one. So the geometry got merged together, which really matters, especially on more not so efficient embedded devices, with a not so powerful GPU. So we just do less draw calls, fewer draw calls. And I mean, this was a quite big thing when Qt 2 got introduced, first targeting phones and later embedded devices, to really have this ability to work well with APIs like OpenGL. Because of course the OpenGL paint engine of QPainter was not this clever. It could be improved, but yeah, it was never really taken to this level. So this is just a recap. So here I'm showing a much more complex Qt Quick application. This is one of the old demos from 2012. And you can see the scene graph is a lot more complex, but the concept is the same. In the QML, we have a scene graph, and the renderer generates OpenGL calls. Yeah, this is the same thing, showing the batching. In this case, it shows that, OK, there are 4 independent text items in QML, but that's still one draw call because they were merged together. Now, OK, that's the end of part 1. Now I would just mention a few more things we need to work on with graphics, because the story doesn't end here. So sometimes there are these misconceptions that OpenGL is cross-platform and that will work everywhere, so you don't need to do anything else to make this work on a random embedded device. Well, I mean, it's true because Qt hides this from all of you, but hides this all from you. But it's not that simple, because, for example, under OpenGL, we have the APIs like EGL, GLX, WGL, which is EGL is a Chronos standard, which is the interface. So you need something to manage the context and create surfaces. So really, it's some sort of interface between OpenGL and the underlying windowing system. But of course, GLX is something similar, originated from X11, then VGL, WGL, and something on Windows. On, of course, Mac, you have your own stuff. Even newer APIs, we're going to talk a bit about Vulkan later, have similar things. So there are the platform-specific bits. So you know how you create a surface, you need to connect it to some native object, which is in Windows, probably an HVND, a window handle. I mean, on other platforms, that's who knows what, something. And to make life more fun, under this, so if you are on a platform with a windowing system, this is where it ends. This is where Qt's responsibility ends. But if you are an embedded without a windowing system, then you need to deal with yet another layer of things, because EGL on its own, that's of course not sufficient to really output something, because you have something like EGL, create window surface. So what matters here is that it has a native window, which is something. In the worst, it's platform specific. If all else fails, it's a void star. But of course, it depends on the graphic stack what that native window handle is. So of course, this is why we end up with things like, looking at the Qt source tree, you have things like, these are platform plugins. So you see there's something for Windows, something for XCB, then something for Mac. So there was this EGLFS, which we often use on devices where there's no windowing system. So what happens here is that this is a plugin to Qt. But of course, the plugin itself has a backend. But of course, the backend needs to have multiple backends. So we have more than 10 backends to the backend just to make it work in various setups. So for example, on a simple case, in the old days, on a Mali-based Linux device, Mali GPU from ARM, the native window handle used to be, you just had to know, it was a struct with 2 shorts. And then this is what you could pass to EGL create window surface. Or of course on Vivante, that's another company doing GPUs, IMX6, IMX8. So their GPUs are used in NXP's SoCs like the IMX6, IMX8. There you just call some random functions provided to you by Vivante, FB create window, we don't know what it does, it returns something, and we can pass that to EGL create window surface. Or, of course, on a Raspberry Pi, when we use the default Broadcom stack, then we use this Disman, which is a proprietary API to manage layers and composition. So there we create a layer, and then the handle to that layer will get passed to EGI create Windows surface. And in some cases these days, so there is a certain convergence device on Linux, at least using the DRM, so direct rendering manager and kernel mode setting, which is a nice API. It can do a bit more than this, because now you have a way to enumerate connectors, so we can handle multiple displays. The downside is that even that has two variants, because then there's two different buffer management strategies, depending on are you part of the open source world or are you NVIDIA. So yeah, this is the GBM versus EGR stream thing, if someone is familiar with that. But that doesn't matter. The point is that, yeah, multiple backends and variants everywhere, which is, oh, and of course, QNX has its own thing, own API to manage all this, and so on and so on. So there's a lot of interesting things to do in the graphics team in Qt. So, OK, this is just demonstrating the concept. So again, our favorite application running on Windows. This is taken from an old blog post. So that was a Tegra K1 development board, I think the automotive version, which is the earlier iteration of NVIDIA's stuff. And then the same application running directly without a windowing system, so a full screen app. And then this is a bunch of Qt applications through Wayland. So of course here's a compositor which composes the output of these other Qt applications together, is also a Qt quick application. So yeah, this is the more complicated multi-process or multiple visual process story. Now, in real life, it's good to remember that things get more complicated, because in automotive, things are not so simple. So you don't just have a Raspberry Pi and boot into a Qt application and ship it, because there are all sorts of systems when maybe you run multiple OSs on one board. So there is some hypervisor involved. So for example, in this is taken from a video from one of our demos at some show. And it's pretty cool, because it's a relatively powerful Renesas board with a PowerVR GPU. And of course, there's presumably some sort of hypervisor. So you have two partitions, one running Linux, one running Integrity. So of course, one of the screens is a Qt Quick app on Integrity, whereas the other thing is a Qt Quick app on Linux. And of course, this can have all sorts of problems of its own, because hypervisor, yeah, then graphics is probably virtualized. And of course, who knows, maybe it has limited support, maybe it only supports OpenGL 2, and maybe it has all sorts of quirks. So yeah, lots of things to deal with. Why is this here? So yeah, just to have something completely different, this is WebAssembly. But anyway, I think we have some similar demos at our booth out there. So yeah, which is an interesting thing. So here, this is a Qt Quick application, and of course, we still render with OpenGL, but of course, in practice, that will become WebGL in this case. Yeah. So going up, we have, of course, lots of OpenGL stuff here and there in Qt, QOpenGL context. Of course, we need to manage the resolving of functions, which is not so easy, because you often can't just call a GL whatever function. You might need to resolve it dynamically for various reasons. And yeah, of course, Qt needs to take care of that stuff. And of course, there are, especially in embedded space, we have these things quite often that, the graphics stack, so the driver which you get from somewhere for the GPU on that board, of course, it may not work that well in all respects. And of course, in some cases, we just need to work around things. So just disable using whatever uniform buffers, because the board support package has a pre-alpha debug build of the graphics driver, which is too slow when using uniform buffers. And of course, it could be that you can never update that BSP, because you would need to go through multiple layers of companies and 10 layers of management. So what you do instead is that, yeah, unfortunately, what people do is that maybe just make it so that we can live without that feature. So just don't use uniform buffers on that particular device, on that, with those drivers. Yeah, well, this is just showing things, because I've talked about applications like widgets, Qt Quick, but of course there's a third one. You could just create a simple Q window and then render OpenGL content on your own. So this is pretty rare, I think, so I don't think anyone does Qt applications like this, but this is done internally during development a lot. So this is the use case which you can do with other libraries like GLFW, if you just use the if you just use the core parts of SDL, that you just get a window and then you do your own OpenGL rendering in it. But this is essential because this is what Qt Quick is built on. Okay, no need to spend too much time on widgets because we saw QPainter and all that stuff in action. So the main backend for QPainter is the Raster paint engine, which is used by widgets in most cases in Qt 5. Yeah, and the OpenGL paint engine still exists, but now it's a bit aging. So we'll see what we do that with in Qt 6. Qt Quick, well, we saw, so QML, that's a language. Of course, it can include JavaScript, and this is where everyone screams, but I don't want to use JavaScript. But of course, you don't have to, because in many cases, Qt Quick applications still do business logic, and most of their things in C++. QML is used to easily describe the UI. But it's important to note the distinction between QML and Qt Quick, even though we use this kind of interchangeably, because QML is just the language and the engine, and Qt Quick is a library that provides these types like item, rectangle, image, providing animations, positioning, input, whatnot. So really the visual, the graphical things. Yeah, well, we saw an example for rectangles, so we probably don't need this. I just usually like to highlight the main things that this stuff is nice because you had property bindings. You can you can animate properties, and it also has a component model. So of course this is a full QML document. But you could of course also make this, put this to a file, name it something, and then instantiate in another document. So of course you can create one object tree at runtime from several files, which is great because in big companies often different people want to work on different parts of the UI. And yeah, sometimes some other frameworks, like we have some horror stories in the 3D solutions used together with Qt, if they don't have this, they can only have the entire 3D scene in one XML file, for example, then some of the users will have serious problems because they would like to work on different parts of that scene independently. But of course, if the thing doesn't have the option to load up the object tree, the scene from multiple files at runtime, then that's not possible. Oh yeah, well, yeah, just under a screenshot of our favorite demo. So this shows things like shader effects, particles, and so on. So things Qt Quick is good at. Qt Quick Scene Graph, I think I have shown the main idea behind this. You remember that graph tree with the transform nodes and geometry nodes. And one interesting upcoming thing is that we will have yet another 3D solution in Qt. This time, this is called Qt Quick 3D, which has nothing to do with Qt 3D and has something to do with Qt 3D Studio, but it's not that. So the idea here is that finally in Qt 6, what we want to see is that you have 2D and 3D described in QML in a more unified way. So of course this is just an example. I'm not sure if this is how it will look in the end, that you have light, camera, model. Of course the things have materials on it. So this is really aimed at creating these mixed UI. So you have 2D elements, and then maybe there's a car model or something. That's typical in automotive. So there's 2D and 3D combined, but the 3D parts, of course, not that complex. And of course, this really starts shining with the designer story, because for Qt 6, another goal is that in Qt Design Studio, what we want to see is that you can design both 2D and 3D in the same tool, so you don't have that what today, that you do one thing for your 2D UI and then you use another tool, say Qt 3D Studio for 3D, but to bring this together. So it's kind of one tool, and yeah, we'll see how this works out in practice, but it's gonna be kind of cool if it really materializes in this form. Okay, yeah, well, there are other ways to do a button in Qt, but there is absolutely no time to talk about things like Qt Web Engine. So there's Chromium under the hood with lots of graphic stuff. And of course, you could do a button in HTML5, integrate it into your QWidget or Qt Quick UI. Yeah, I don't know why, but sure. And of course, the MCU story. Yeah, you can come to our booth and see some good examples of the latest Qt on MCU story. And to summarize all this, we have a diagram, because You know, sometimes people say that serious things need a diagram. Yes. So this is what we talked about, that really how do we go from the top that you have a Qt application, you go to Qt, there's a scene graph. Of course, eventually you will end up in rendering with OpenGL to a Q window. Of course, under the Q window, you have all the interfaces, then the platform plugin, and then you have all this plumbing eventually, which of course depends on the platform. With widgets, it's similar, but now you use widgets. Of course, there's no OpenGL stuff. And of course, if you just have a Q window, then you would enter on a lower level. So of course, you don't have neither Qt nor widgets. So how does this change in Qt 6, like this picture? Well, it doesn't, or really it should not, because we can't really afford to change this in a big way. What we can do is to do cleanups and change certain aspects. And one thing what we want to do is to get rid of the direct OpenGL usage. So what's going to happen here is that GL whatever cause in Qt and elsewhere will disappear. Instead, that will be abstracted behind some simple, abstraction layer, which we call the Qt rendering hardware interface. So this is this RHI thing. There's quite some talk about that here and there these days. And the goal is that we should be able to run on other graphics APIs. So, Vulkan, Metal, Direct3D, and of course, OpenGL stays an option too. The goal here, so this is not done because of to gain performance. This is to ensure that the Qt everywhere story stays true. So sometimes people think that Vulkan, they will get great performance improvements in their Qt applications when running on Vulkan. Of course, that's not given because in many cases, it might just be so simple that you don't gain much. It could be that there are some gains. It could also be that in some cases we will be slower, we'll see. But yeah, the goal is really just to be able to run everywhere. So the details we are not going to go into. So this is just a screenshot of the documentation. So I was stupid enough to write documentation for this RHI thing. The problem is that this is going to be a private API. So this is not going to be exposed to applications, which of course means that the documentation is not really used because it won't be part of the Qt docs. But yeah, well, what can you do? Who knows what WebGPU is? One, that's good. Or of course, it's also the implementations like Dawn from Google, which is the implementation of that. That would just be interesting because if you know that, then conceptually, what we have, these QRHI classes are quite similar. So there's quite a lot of match between the way things work. So the goal is not to really wrap all of Vulkan or Metal. It's just to create something that's sufficient for Qt's needs, and it can translate still to these various APIs in the same way. So currently we support OpenGL, D3D11, Metal, and Vulkan. Yep, we're going to skip all this since, yeah, there's no point in jumping into this. But what this shows is the Qt scene graph renderer and the old, or before and after. Well, actually, you have both in the code base. So the key here is that this GL whatever that disappears, and instead we have now things like command buffers, and then we record raw codes there. Or we also have to deal with things like, we have pipeline state objects, so no individual GL states change blend state or no GL enable. So this whole OpenGL state machine things gets forgotten. Instead, we work in a lot more data-oriented manner. For example, we build big pipeline state objects, which include everything from the shaders and all the states in one object. And the final thing is shaders. Just to give an idea, we will have solutions for shaders. So these are vertex shaders, fragment shaders. Qt is full of these. And we already have some issues in Qt 5 that we need to have at least 2 variants for the different OpenGL versions. Also, in some of the new APIs, you can't compile shaders, you can't get reflections, so you can't dynamically discover what are the uniforms, what are the vertex inputs. And of course, things like shader effect kind of needs this when you have user-provided shader code. Plus, there is something that Qt likes to rewrite vertex shaders, like add a few lines for various reasons when it does the batching, and which means that, of course, that only really works for GLSL. And of course, yeah, we don't have that for Direct3D. We need HLSL. For Metal, we need the Metal shading language. So what we are doing is that we are kind of using some third-party components. So what we are doing now is that we take our Vulkan style GLSL, do the rewriting, if we need that, and we use GLSlang, which is an open source project, so which compiles GLSL to SPIRV. So SPIRV is this bytecode, which is a standard, another standard from Kronos. And of course, Vulkan can use SPIRV directly. But for the other APIs, we go through SPIRV Cross, which is another library. And that's pretty cool, because what we do with it is that we have the SPIRV bytecode as input, and it can generate various GLSL versions, HLSL or metal code. That's pretty human readable, even the output. And we also get the reflection at that stage. So things like what are the uniform buffers, what are the members, what are the offsets of those members. And then the current pipeline is based on this. We pack it all together, put it to a file, and at runtime we will deserialize it via this QShader, which is a simple container. And then the RHI will pick the right version, right variant. Oh yeah, this some script that just shows the concept. So here is one of those shaders we've seen before. It was converted to Vulkan style. Now we have beautiful location binding qualifiers. We have a uniform buffer, and then we run it through some tool that spits out a binary blob. Of course, this is the dump of the binary blob in human readable form. You see that we simply have multiple versions of the shader. Of course, there's a SPIRV binary, the bytecode, and GLSL, HLSL metal stuff, and together with all the reflection that it has one uniform buffer. Here are the members and the offsets. So this is pretty cool and works pretty well in practice. And I'm almost done, because these two things, the RHI and the shader story, well, basically this is the foundation of everything right now, when it comes to moving away to direct OpenGL usage. So when will this be available? So of course, we actually do this before Qt 6, at least some parts, because at least I don't really believe in this, that we will just wait until Qt 6 and do everything is one go and it will be fine, because yeah, things usually don't work out that way. So instead, what we've been doing is that when it comes to the Qt Quick port, so forget other parts of Qt, for Qt Quick specifically, we did the ports side by side. So we have both in the code base, and this will ship in November in Qt 5.14. And of course, by default, nothing changed, but you can opt in if you want to, either with an environment variable or also from C++. So the thing here is to get, of course, feedback from people who are interested early on, and then evolve this. So really the thing ships and it's out there in the wild earlier than November 2020, which is the current target for Qt 6. So I think this is a pretty good move to, really start doing things side by side and then ship it and then iterate, evolve. Oh yeah, this is just a screenshot from the docs, because we have actually the top, you can enable this by setting an environment variable called QSG RHI, and then magic happens. And then, yeah. And finally, yeah, but for Qt 6, I will note that, of course, Qt Quick is just one thing, because then we need to think about similar porting work for this upcoming Qt Quick 3D. Then what do we do with QPainter? We still have an OpenGL paint engine. Do we want an RHI paint engine, for example? What is that good for? And in Qt Multimedia, maybe Qt Location, there is OpenGL usage all over the place. So yeah, it's quite exciting. We have some quite exciting times ahead to see, what we do with all that. All right. So that's it in short. Unfortunately, it's not really possible to go into the details, like all this, how do we, what do we do with Vulkan metal and whatnot. But I think this gives an idea that, the things we are focusing on at the moment. Of course, widgets are still there. They are not going to go anywhere. And of course, Qt Quick for 2D. Also, the 3D story will be improved further. And also, we are trying to ensure that Qt and Qt Quick and all that stuff runs everywhere. So even if OpenGL disappears, then we'll probably be fine. Yeah, thanks. I think we are kind of out of time. Anyway, but yeah, I think if there are questions, we're gonna just take them separately.